So now let's look at the thermodynamic properties of fluids. So as we take a look at this, so our properties are kind of binned within three major categories. The first is within the velocity field. So these are the most dynamic of those thermodynamic properties of fluids, and they are the pressure, the density, and the temperature. So we go beyond that. We also have the heat, work, and energy properties, internal energy, enthalpy, entropy, specific heat, based on constant pressure and constant volume, all that stuff that you've got from your physics class and your thermodynamics class. And also what we call the transport properties of the fluids. And that's really the properties that deal with how fluids move. So we have our viscosity, which we'll be talking about during this week of lectures, but we also have the thermal conductivity, and that really comes about from the convection heat transfer, which is a heat transfer based on fluids moving. Now, the thing is, for this class, we're not going to be worrying about enthalpy or entropy, and we're not going to be worrying about thermal conductivity. So we only have 6 properties that we're really going to go over in this class. So let's start taking a look at our pressure. And let me change my pen from the red that we have. So a couple things about pressure. Pressure is, aside from velocity, it's the most dynamic of the properties. And what we're going to do is we're going to base a lot of what we do around standard pressure. Now, what standard pressure is pressure at sea level. And then everything kind of adjusts from there. So standard atmospheric pressure at sea level would be 1 atmosphere, which is equivalent to 2,116, I don't know why that spikes there, let's redo that, 2,116 pound force per foot squared. And it's also 14.7 psi, and that's also 101,300 Pascal. Now, it seems like a big number, but a Pascal is exceedingly small. We've talked about newtons. What a Pascal is a newton over a meter squared. So you're looking at basically a quarter pound over 9 square feet, which is pathetically tiny. So as we talk about pressure, though, we have a couple of different kinds of pressure. And basically that falls into what we call relative pressure and absolute. And so basically absolute pressure is keyed to a vacuum. So that 14.7 psi of atmospheric pressure is keyed to the vacuum, so that's 14.7 psi above a vacuum. Relative pressure is keyed towards atmospheric. So the relative pressure, or what's called the gauge pressure, it's called gauge because it's what's read off most gauges, is comparing the pressure that you're at currently to whatever atmospheric pressure is. So here at sea level, our gauge pressure would be 0, which would be 14.7 psi. If you went to Denver, which is a lot higher in the air, the pressure there is about 8.7 psi. So the gauge pressure of 0 in Denver and the gauge pressure of 0 at sea level, they'd be the same gauge pressure, but they would have a different absolute pressure. So actually, if we look at this little chart here, this kind of shows us what's going on. This line right here is atmospheric pressure. This line down here is our absolute zero pressure, or our vacuum. So between these two lines, from here to here, that would be our pressure of our atmosphere. Anything above the atmosphere, as you can see from this line right here, that would be our gauge pressure. So as you're looking at it, if you've got, say, this little dot here, that's the pressure in our tank. So the pressure in our tank would be the pressure of the atmosphere plus our gauge pressure. And so you'll see this quite a bit in this class. You'll have to be converting between absolute pressure and gauge pressure. So typically what happens if we have something in gauge pressure, the problem will say the reading on the gauge is, or you'll see things like PSI gauge or Pascal's gauge to let you know that you're dealing with gauge pressure. So one other thing to note here is this one here called vacuum pressure. All vacuum pressure is a pressure below atmospheric pressure. Okay, so now let's look at temperature. In temperature, we also have the absolute and the relative gauges. So, starting out with the relative gauges are all based on the boiling and freezing of water. So, in the metric system, you have the degree centigrade or degree Celsius, and that runs from water freezing at 0 degrees centigrade. And then it boils at 100 degrees centigrade. So that's a pretty easy thing to remember. In the in the English system, we have the degree Fahrenheit. Water freezes at 32 degrees Fahrenheit and then boils at 212 degrees Fahrenheit. Then we have our absolute temperatures. In the metric system, we have the Kelvin. And one thing to note, it's the Kelvin, not the degree Kelvin. It's the only one that doesn't have that degree symbol for some reason. And to convert from Kelvin to centigrade and back, it's Kelvin is the degree centigrade plus 273. It's technically 273.16, but we're fine with that. In the English system, we have the degree Rankine. And the degree Rankine, to get that, is the degree Fahrenheit plus 460. Once again, it's technically 459.69, but it's close enough. So it's kind of, I saw an interesting meme that was talking about the unit systems, and it's kind of funny. It's why the English system's better. So if you look at English and you go from 0 to 100, you've got cold and you've got hot. So that would be Fahrenheit. And then if you look at degree centigrade and you go from 0 to 100, you've got cold and dead. And then if you look at Kelvin from 0 to 100, you've got you're dead at 0, you're dead at 100. So those absolute temperatures, 0 Rankine, 0 Kelvin are the same thing. And that is pegged to what's called absolute zero. Absolute zero is the place where all atomic motion stops. Back when I worked in the high energy physics, the coldest that we can get anything was down to about 3 degrees above absolute zero. I'm not sure if that's still true now, but it's cold. So the last thing that we have to do is look at density. And we're all familiar with density. What we know what density is. Density is mass per unit volume. Of course, this is fluids. We have a couple different kinds of densities that we're going to be using. So a couple things to note. Density is highly variable in gas, and it's almost proportional to its pressure. Density is nearly constant in liquid. We typically treat liquids as incompressible. Liquids, that's not necessarily true, but it's close enough. If you look at water, it takes about 220 times the pressure of atmosphere to compress water 1%, but we still use that to say, okay, it's generally incompressible because it's really hard to compress. So let's start out. We're going to continue your classical Greek education. That is lowercase rho, and that is for density, and density is mass divided by the volume. Now you'll see that when I'm writing volume, I write this little bar through my V's. That's a typical fluid mechanics thing to separate velocity and volume. So anytime you see that V with the bar in it, we're talking about volume. And so if you look at this, well, we're going to have units of mass. Volume will be units of length cubed. So what I'm doing here is just showing what the units are. This is a typical fluids thing, especially when you're putting together dimensionless parameters. So basically you pick your unit system, you just plug that stuff in. So in the metric system, mass would be kilogram per meter cubed, and then the English system, it would be the slug per foot cubed. Now we do have two derivative properties of fluids, and the first one's what's called the specific weight. And the specific weight is denoted by, continuing your Greek education, the lowercase gamma. Now, out of all the Greek letters that I will be giving you during the course of this class, this is probably the one that does not look as much like the book as it could. It's the one I have the most trouble with. You'll see it when you look at it in the book. And so, what is the specific weight? Specific weight's pretty easy to calculate. Its specific weight is our density times our gravity. So it's giving us a weight per unit volume instead of a mass per unit volume. So what you could do is the units for this guy are going to be force per length cubed. So now you're looking at newtons per cubic meter. You're looking at pounds force per cubic meter. This will occur frequently in pressure calculations. And the third one that we have is what's called specific gravity. So specific gravity does not get a Greek letter, it's just SG. And so specific gravity is a unitless parameter, which means that there are going to be no units associated with it. And the reason that is what it is it's the density of the fluid that you're dealing with divided by the density of water at 4 degrees C. And since it's density and all specific weight is density times gravity, you could also say this is the specific weight of your fluid divided by the specific weight at 4 degrees C. So this one's useful. You'll see specific gravity a lot, especially in motor oils and things like that. If you were ever a bartender, which I was in college, you will have a nice little bartending handbook. And that bartending handbook gives you the specific gravities of different fluids, so you know if you wanted to make a layered drink, how you can load those up. Now the question is, why 4 degrees C? That seems kind of an odd number. Well, 4 degrees C is where water has its maximum density. Because now you're getting to that point where it's getting ready to start to freeze. You've cooled it down enough that this is before it starts to form ice crystals. And so the density of water at 4 degrees C, so density of H2O at 4 degrees C is going to be 1,000 kilograms per meter cubed. I typically do that one in the English unit because that is the one that typically do this one in the metric unit because 1,000 kilograms per cubic meter is pretty easy to remember.